Phase 1, liftoff. First, we are asked to get the acceleration necessary to arrive in the desired time. With this, we will be using the formula of final distance equals initial distance, that will be 0, plus initial velocity times time would be the initial velocity will be 0, plus acceleration times time square over 2. The final distance will be 150 kilometers, and in meters is gonna be 150,000 meters. This will be equals 8 times 180 square over 2, and the acceleration will be 9.2592 meters over square second. Then we are asked for the energy required to get there. For this, it would be the kinetic energy, so we have to get the velocity, which would be equaling the mechanical energies, and the masses will be cancelled, and the final velocity will give us 1,715.5172 meters over second. Then we substitute in the formula of kinetic energy, and we get that the kinetic energy will be 8.
Phase 2, directional adjustment. It's a parabolic throw, and we had to divide in y and x axis to get both the vertical and the horizontal displacement. And for the speed, we used this formula.
Okay, so now for the third phase, which is decoupling, we are asked for 3 things. First, the type of movement that the rocket follows is a parabolic movement. It does this. And to calculate the time it takes to reach 400 kilometers from phase 2, we use the formula of time equals final velocity minus initial velocity divided by acceleration. So our final velocity will be 0, and we will subtract the initial velocity, which will be the final velocity from phase 2. So in this case, it is 1,715.5172, and we divide that by the acceleration in negative, that it will be in this case 5.88, because we're considering the 60% of gravity acceleration, that we know that the normal acceleration is 9.81. So in this case, since it is only the 60%, it is 5.88. And that's how we get the time, which is 291.4572. Now for the horizontal displacement of the rocket, we just have to subtract the 400 kilometers minus the displacement of the second phase. So we will subtract 400 minus 157.0253, and this equals 242.9747 kilometers. Okay, so now this is phase 4, and it is called re-entry. And we are asked what is the acceleration of the fall and the type of movement that the thruster follows. Basically, it was pretty simple, since we know that the rocket is going downwards, so it will be free fall. Therefore, the acceleration of the fall will be 9.81, which is the normal acceleration of gravity. So it is free fall. And lastly, we're asked the speed at the end of this phase, and we calculated this through energies, through mechanical energies. So we used the formulas of using the mechanical energy, which will be potential energy plus kinetic energy, and that equals to the other mechanical energy. And we basically canceled in the whole formula. We stayed with the potential energy equals kinetic energy of the other side. So by calculating this, we were able to calculate the speed, the velocity, and which was 2,801.4282 meters per second.
Last phase, the landing, we're asked for 2 things: the acceleration with which the rocket must compensate to land and at the desired speed, and the distance from the launch base at which the thruster rescue team should be located. For the first question, we're asked for the acceleration, and we're going to use the formula of final velocity square equals initial velocity square plus 2 times acceleration times the final distance minus the initial distance. in which the final velocity will be 0 because we're landing. The initial velocity will be the velocity from the last phase. The distance will be the final distance, that will be 0, minus the initial distance, that will be 400. So we get minus 400, and we pass divided that, and the acceleration will be 9,809.9999 meters over square second. And for the distance, we're going to use the formula of final distance equals initial distance, that will be 0, plus velocity in x, because we're talking about free fall, times time, plus acceleration times square time over 2.